Ladies and gentlemen, please join me in welcoming Dr. Greg Harris.
The digital thread, digital tapestry, digital quilt, digital twin, model-based enterprise. These are terms that we use often, but do we really know what they mean? How do you know what to do with them, and how do you manage them in your own operations? The Industrial Internet of Things offers the opportunity to engage real-time management of operations. How do we implement these capabilities to improve and optimize our operations? So today we have the good fortune to have this esteemed panel with us to lead us through a conversation on the digital twin and the Industrial Internet of Things. So I'm going to introduce each of them and then let them have a moment after the introductions to make their comments. So starting at my far left, your far right, Dave Riemer is the Vice President of Aerospace and Defense Strategy for Siemens PLM software. He recently joined Siemens PLM following a 35-year career in aerospace and defense in various leadership positions. David is responsible for utilizing all resources at Siemens PLM software to provide value-added solutions to the aerospace and defense industry. Before joining Siemens, David was the Vice President in Science and Engineering for ATK Aerospace Systems, where he was responsible for the technology programs at ATK Aerospace Systems Group, including the successful development of Ares 1 first stage booster, culminating in the successful static test of the world's largest rocket motor. He was also responsible for all engineering activities on the Space Shuttle reusable solid rocket motor, missile defense systems, strategic missile, and commercial satellite solid rocket boosters. Prior to joining ATK, David had a 27-year career at Raytheon Aircraft. His last position there was Vice President of Product Development Engineering, where he was responsible for all product development and airworthiness of all Raytheon aircraft. Prior to this assignment, David was the Vice President General Manager, Government Business Division, specializing in military trainer aircraft, including the Air Force and Navy T-6A Texan II, the Navy T-34C and T-44, and the Air Force T-1A, and special mission aircraft for U.S. and foreign government customers. Prior to this, David held various leadership positions, including Division Manager, Target Missile Business and Manager, and Cryogenic Business. David started his career at General Dynamics, Convair Division, as a thermodynamics engineer, having worked on several large superconducting magnet designs, cruise missile, and Air Force space antenna studies. He earned his Bachelor's of Science degree in computer science with minors in mechanical engineering and finance from the University of Utah, and Master of Science in Mechanical Engineering from the University of Utah. Second, I have Jeff Smith. He is the Director of the Aerospace and Defense Ideas Lab at Dassault Systems, with a career spanning over 34 years. Jeff has proven results driving disciplined change in all aspects of product lifecycle. He is an inspired leader, energizing both internal and external customers through strategic and critical thinking, and adopting and pioneering new business processes and product improvements to enhance affordability. Mr. Smith retired from Lockheed Martin Corporation with over 27 years in various positions, including program leadership and management, critical transformation, business capabilities, enterprise processes and tools, engineering and manufacturing, testing, launch support associated with engineering, IT, technical operations, engineering process improvement, GPS 3, Titan 4, Titan 2, commercial Titan, and NASA shuttle programs. He holds a bachelor's degree in civil engineering from Brigham Young University. And then finally here to my left is Avner Ben-Bassat, the president and CEO of Plataine Technologies, a leading provider of industrial internet-based intelligent automation software solutions for aerospace manufacturing. Partnering with industry leaders such as GE, Siemens, and Airbus, Plataine leverages the IoT and artificial intelligence technologies to push the productivity envelope, reduce cost, and weave the digital thread to improve quality and traceability. With over 15 years of experience in the field of complex multi-dimensional optimization software for the services and manufacturing segments, Avner leads Plataine's total production optimization, product vision, and global business strategy. Avner holds an MBA with distinction from Duke University and a Bachelor of Science in Mathematics and Computer Sciences from Tel Aviv University. So with that, Avner, would you like to start with your comments?
Sure, thank you. Well, good morning, everybody. Thanks, Greg, and here for AeroDef for hosting us here, and our team here on the deck. Our company, Plataine, we specialize in automation and optimization software for manufacturing. As Greg has mentioned, we leverage a set of technologies, including IoT and artificial intelligence, with the goal to help improve production efficiencies and improve quality. We work in a number of industries. Aerospace is our fastest growing one in terms of adoption of these technologies. And we work with customers in production such as GE and Airbus, Triumph, Israeli Aircraft, and a number of them globally. We're also very proud to partner with industry leaders such as Siemens and Dave's team here on my left, GE, and also in the more research settings like Airbus's CDC organization in Stade in Germany, as well as the AMRC with Boeing in Sheffield in the UK. When we talk about these technologies, you know, it's cool, right? But I don't think anyone here in the room bought an enterprise level system because it was cool. So we're always looking for the outcomes, the benefits, you know, the real hard numbers that are driving the value behind this. And that's what we're seeing in the field. And we're seeing how this technology, which is so much talked about, when you take it from the lab, from the research center to real production with all its real challenges, it brings real benefits in automation, throughput, better quality, reduction of cost of poor quality, and other such metrics. And these are the topics we'd like to cover here today.
Great. Jeff?
Yeah. It's great to be here at this conference, and I see a lot of familiar faces. I have a great opportunity working with Dassault Systems. I have a CEO that is all about sustainable innovation and harmonization of product nature and life. So when you think about the Internet of Things, you think about the digital twin, or what we call the 3D experience twin, the opportunity to create this virtual system, this virtual product, and all the associated processes before you create them in the physical world. And so it's very exciting to be part of what's happening on the earth today, and be able to work with different industries. Of course, my focus is aerospace and defense, but just to be able to take these rich capabilities that are there for us and be able to stitch them together, and then being able to see the benefits and to create that value for our customers. So one of the other things I get to do is all about ideation and creating centers, innovation centers around the world, to be able to express how we can leverage these different capabilities and integrate them together to create that value for our customers.
Thank you. Dave?
Sure. So Greg introduced some ideas of the digital twin, the digital thread, big data, Internet of Things. So at Siemens, we're really trying to bring that all together in what we call digitalization. So we not only want to have that digital twin to be able to virtually represent not only the product, but the plant, the process, the in-service performance. And that's going to give us the baseline for us to reference the real data we're collecting from the Internet of Things, right? It doesn't do us any good to measure something if I don't have what I expected it to be. What did I expect the performance to be? So that virtual twin, the digital twin, so critical. But without a digital thread tying the information together, the digital twin answers kind of the question of what is the plant, what is the product? But if you want to know why is something what it is, why is that plant running that way? Why is the product performing that way? The answer is you really need the digital thread to be able to tie that information together. And all of those are basic principles of really the Industry 4.0 initiative, to which Siemens is a big participant in, bringing all that data together and being able to convert data, large data, into small information, making the data understandable so you can make intelligent decisions around it. So that's kind of our focus right now, supporting aerospace and defense.
Great. So make sure you're texting in your questions for the panel. Start off with a couple of questions here, and I'll start with Avner and give you each of the others a chance to answer also. So, this is quite an endeavor to try to take on developing a digital twin and utilizing all of the capability of the Internet of Things. So what operational outcomes and benefits have you seen driven by the industrial Internet of Things technology?
Okay. I think the best way to answer this question is first understand the problems that we're trying to solve. When we approach this, when we're in dialogue with our customers, we try to address a real problem or something that's painful. And Andreas here in the earlier session talked about a problem which I believe is very common here. With rates going up and cost pressures further increasing, how do we deal with that? We see processes that are not built for this kind of environment. A lot of paperwork, loosely integrated systems, and that's really making things worse in terms of visibility, cost controls, and the ability to scale. So when we approach these problems, we try to understand how can we address them better. Now, in this respect, the IoT and the digital thread, et cetera, are enablers. We want them to leverage them and make things better. In terms of the specific outcomes that we are seeing, we are measuring, we see them in, let's say, two main channels. One is operational, and I'll explain what I mean. Real results in terms of KPIs such as increased capacity, increased productivity, reduction in waste, whether it's direct waste of material or waste of cost of poor quality when you scrap an entire part. Beyond that, there's also the benefits around quality. The digital thread allows for far better quality control and traceability, not just for identifying the bad part, but also understanding why it had happened. And of course, there's the auditability aspect, which is more formal or regulatory. So the benefits we see there are very concrete, and we're seeing them evolving. With every day that we work and every day that we solve a problem, we're able to see the next horizon, the next goal. So we've reached this level, now we can take it on to the next level.
Any other panelists like to take a shot at that question?
Good.
Sure. So I think, one of the things about Siemens is we do an awful lot besides software. So we do an awful lot in the plant management, power management. So one of the things we've seen a big improvement in from the Internet of Things is this being able to intelligently operate your plant from a power perspective to minimize your peak power demands. And I think we have seen tremendous improvements there. I think product-wise, we've seen an awful lot of data and information coming back. But now the real key is we're able to associate information, right? So we can not only look at, say, failures of a part, but we can now understand that failure of that part. It seems to be occurring when this particular item operates, say, in a certain environment, right? And that's unique in the ability to be able to tie that together. As an engineer, we would have known the part failed, but we'd have had no idea where it was operating, et cetera. So I think this better understanding of what's really driving performance, whether it's the plant or the product, is really the benefit of the Internet of Things.
Okay.
Yeah, so what we did is we took what was happening in industry and we said, okay, if we can create experiences that are specific to a particular industry, so like, for example, in aerospace and defense, we created these industry solution experiences from conceptual design, so being able to create this virtual twin of the product and all the associated processes, and then be able to create what we call our co-design to target capability, where we get into the detailed design, and then creating what we call the virtual factory, so that we could take, leveraging the Internet of Things and big data analytics and so on, being able to bring that back into the whole factory of the future concept, leveraging ideas from Industry 4.0 and so on. And then being able to take that virtual factory and those results that are coming from what I call the sensing factory, and then bring them into the execution of that factory through what we call build operate. And then being able to take that data and then bring that into what we call our license to fly from a certification standpoint, and then being able to manage the MRO, the support, through our, what's it called? I can't even remember what it's called now. Through another industry solution, and then ultimately being able to stitch all that together so that you have this living factory concept, this living system, leveraging the digital twin with the sensing data coming from the Internet of Things.
Great, thank you. So when it comes to digitizing the factory, how does the digital thread contribute to improved quality and auditability? Avner, you want to start?
Yeah. Well, when we say the digital thread, we're looking at it at a much wider perspective. We use a lot of the terms of genealogy and inheritance, and I'll explain. When you take a number of materials and you create a part or a kit, we would say these materials are the parents, and the kit is the child. And you take a number of kits and you make a part, and then hence you have the grandchild. And by the time the production process is done, we have a lot of generations, many generations of an assembly that has happened. And alongside that, we have the thread of the entire family tree. But if you think about it, it's not just the materials that went in, it's every other operation or environmental status that went into it. And every one of those leaves its little DNA mark onto that product, whether I built it or Joe, whether it was done on station 1 or at station 2, whether it was done at 20C or 21C. And the more information we attach to that web of threads is what gives us a very powerful data structure on which we can operate. And now, to answer the question, that gives us a massive opportunity for improvements, whether it's leveraging analytical techniques from the fields of AI or other mathematical mechanisms. We can traverse that web and identify problems before they happen, and then take action, be predictive and then prescriptive about it. The more data we have, the more times we follow this process, the richer and multidimensional this array of information that we have, and we can make even better decisions. So from a quality perspective, just to give two examples that we're seeing, one is the feedback loop with the services organization. I believe you've addressed it as well. A part comes off an airplane, we take it to the lab, we understand that it comes from a faulty material. We need to go back through the web and find the source material, and now find all the other parts made from the same material. A process today that can take weeks and months of paperwork is identified really in a matter of minutes. Another common use case, or this is really the recall scenario. Find me all the materials, all the parts from this material. Find me all the parts that were made by this tool, etc. The second use case is the other way around, moving up the digital thread. We're in production, the material supplier calls in to apologize, there's a defective batch of material. Now we need to find all the parts that are coming from that material. Some of them are in production, some of them are out in the field, and this could take weeks with the current technologies. The digital thread now allows us to find them quickly and take them off the production line for preventive action. So we see these use cases merely by having this sophisticated data structure, even before escalating it to the higher AI means of machine learning, et cetera.
Great, thank you. So we've got some questions here that are starting to accumulate into groups from the audience. So for a company that's on the ground floor of industrial Internet of Things, how do you recommend beginning to eat the IoT elephant? Dave, you want to take that one?
Okay. So let's see, what the normal line for how to eat an elephant? One bite at a time. So I'm a fan of crawl, walk, run. So if you're going to start, you want to start with having the digital twin, right? Before you get all excited about collecting a lot of data from the Internet of Things, start with what's the expected performance. So by that I mean running that simulation of the plant or the process or the product itself. I'd start there, get a real good foundation in my predictive engineering. What do I expect this to do? And then I'd start collecting that information that I need to have in order to be able to validate that model, validate that simulation, and collect that kind of information. So I'd start with the foundation of the digital twin. Clearly, I want to connect all that information together. The prior question kind of around that, what does digitalization do for manufacturing? It's very much the same thing. The objective here is to relate all this information. I want to be able to answer that why question. Why am I doing this inspection? I'm doing that inspection because it's the result of a key characteristic in a design. That key characteristic in the design is driven by a CAE analysis, and that's why I'm running that inspection. Being able to tie the information. So I'd start digital twin, connecting that together with the digital thread, and then collecting my information to substantiate my predictive performance.
Great. Jeff, you want to take
Yeah,
that?
sure. So the approach that we've taken is we're creating these innovation centers around the world. And one of them here locally in Wichita, Kansas, is we're developing an innovation campus. And in that innovation campus, we're creating what's called the 3D Experience Center. And so if you can imagine an 18-hole golf course being replaced with 24 buildings, with 9 of them being partnership buildings. And so this innovation center gives companies the opportunity to bring in a small group and kind of test the waters that are related to what they're trying to accomplish, leveraging the digital twin, Internet of Things, robotics, material science, and so on and so on. So we can bring your small team with a specific project to work a specific issue and provide you the whole infrastructure in this 3D Experience Center that allows you to experience the art of the possible related to innovation associated with these different activities of the Internet of Things, of being able to create that sensing factory, to be able to create that virtual product that is very rich, kinematically correct, a multi-physics control sensing environment. So this is how we've tried to create an environment where you don't have to make that huge investment. You can come and you can perform that experience, do that research, do that demonstration to determine where you want to take it based on the challenges and issues that you might be facing.
Okay. So we have several questions here that are starting to show up in terms of how do your solutions address information security, cybersecurity, DoD requirements, or how's the team looking to initiate IoT solution deployment to begin to address these? So how do you handle the cybersecurity issues associated with the industrial Internet of Things?
Okay. Well, it's a question we hear a lot, and it's a legitimate concern. Our response typically is, let's make this concrete. You know, what are you concerned about? What are the security levels that you're looking to address? If you think about it, a lot of the information we're talking about is quite generic in a way, you know, process improvements or process takt times or material situation. And when we talk about these sensors, they will broadcast, for example, the location or a temperature or the status of a given material or a given asset. So a lot of people are concerned about cybersecurity in the sense of hacking these sensors. But these sensors are basically sending bits and bytes that are not tied to anything that's confidential. The confidential information remains in the main servers, in the internal data center, or whether it's on the cloud. And that's really the core of what we need to protect. Having said that, even today, the main cloud providers, such as Amazon, have ITAR-governed, ITAR-regulated cloud environments, which are, you know, guaranteed to meet these standards. So whether it's done in-house or done on the cloud, the broader industry is now able to protect this information. And in terms of the communication between the sensors and the wider network, and then again, what we see out there is that the sensors really are broadcasting nothing of importance in terms of cyber threats.
Okay. Here's another, just getting back to the terms that we use. Define digitize versus digitalize, and similarly digital thread versus digital twin. Anybody want?
I'll do that one.
Okay.
So digitize. So let's see. Based on that bio, I must be the old guy on the panel because it took you like 20 minutes. Anybody remember a thing called a typewriter? It was this really cool device for you young folk. You'd actually touch the keys, and it gave you instant gratification because the letters showed up right on a piece of paper immediately. It was an amazing device. And then along came word processing equipment. And what did we do? We digitized. What did we do? We just converted what we had on a piece of paper into a digital form. But if you ask yourself a question about that digital form, do I know anything more about the information that's on that page than I did the typewritten page? The answer is no, I don't know anything more about it. I am a fan of cut and paste, don't get me wrong, I love that. It's a lot easier than whiteout and you know, scissors and tape to edit. But digitizing really didn't give us much benefit. And if you look at what we did in aerospace, we're very guilty of, we're a lengthy industry, we've had a long existence, we took much of what we had in paper and we created a digital form of it. We digitized it. We took drawings, we took documents, and we digitized them. And we took the same process we had in paper and we just put it into a digital form. And I think we fundamentally missed, that's the difference between digitalization and digitization. It's really taking advantage of this. It's understanding why is that information in that document, what is it, and what's it related to, what's the design related to. So I think the difference is just having a digital form and being able to really take advantage of the information in a digital form. That's the digitalization.
Okay.
Maybe just add to that, you know, you're taking this data that really is static, and now can you turn it into something that's living, that is actionable, that changes with time based on the environment that it's exercised in. And so I think when you think about where we're going with this whole digital thread or digital tapestry, which we called it at Lockheed Martin, you know, the opportunity to bring the programmatics with the engineering, with the support, being able to bring that all together and create that closed loop system so that you have a system of work that's actually sensing every step of the way throughout, you know, the product development and the product life cycle. So I think it's an exciting world to be part of, to be able to bring all these rich capabilities that together just can create powerful systems of work that enable us to invent the future.
So we've got a couple of questions here that have to do with labor force and skills. What do you do if your labor force is not educated in the world of big data and do not enter data and otherwise unskilled in the world we live in? And how do you avoid overloading the human with data and information?
Yeah, I'll take that. I think that's what we're trying to achieve. We're all human, and we're talking about a growing amount of data, and at some point, it's just too much. Now, what we found is that the more data you have, on the one hand, you have more potential value, right? You can achieve more. We've all talked about it. But then again, for us humans, we have one CPU, and that's all we can do. So now we're talking about massive computing power that is able to crunch it and make something useful. Now we're talking about the labor force or the people. The way we would approach this is like a personal assistants or butlers. We have an assistant for the freezer manager. We have an assistant for the line supervisor. We have an assistant for the floor operator. And they're all very busy people. There's a lot going on, but there's a little something on their shoulder helping them. Hey, this material's about to expire. You know, take that material and rush it to that job, or you may have a quality issue here. So this is where the technology can help. And I don't see this as a concern. I see this more as a man-machine team where the computer helps them escalate the real problems and not deal with all the routine. By taking the routine, those ton of data out of the way and encapsulating it under the hood of a software that's intelligent really drives the value. I mean, if you think about it, a car is a very sophisticated machine, and a Prius is has a very sophisticated hybrid engine. But for us as drivers, as users of that technology, all of that is encapsulated in a very well form, and that's what we should aim to have here as well.
Okay.
Can I make one comment?
Yeah.
I mean, David, you made the comment about taking all this data and then turning it into information to be able to create informed decisions. And I think, you know, the opportunity that we have now is to go from this world of searching, you know, like we use with Google and all that, to a world of suggesting.
Yeah.
And so now we can bring this rich world of suggesting based on all this data that is being sensed and be able to provide that to the benefit of the worker. And the other thing that we're doing, for example, on our innovation campus is that we're tying them to universities. So the idea is that we can bring that university relationship with the industry partners that are on the innovation campus, with a multitude of partners like Dassault Systems, and be able to train that future workforce so that they get to be part of that whole ecosystem as it matures and develops. So by the time they graduate, you know, they would have had that experience both from a classroom, both from a lab, and then, of course, with the mentorship, internship at the company itself.
Great.
So yeah, might as well, might as well jump on the pile. So I think there's a couple things. One thing, the question kind of alluded to, the Internet of Things and all this data, and the workforce might not be able to absorb that. I think that's fundamentally the root cause of our challenge, right? It's not providing tons of data. It's distilling that data down to the suggestion, right? To what is it that's actionable and I should do. And I don't care where you are in the workforce, you can clearly understand that in the context of your job. These are experts at doing that job. They need the data converted to information so they can take action on it. And we participate. Greg was instrumental in getting DMDII started, a joint government, industry, academia facility up in Chicago. It's a terrific place where we have exactly the same sort of innovation center that Jeff's referred to, across the broad spectrum of industry and academia. It's a wonderful facility. If you've not been there, I highly recommend you get to go to DMDII and Greg's vision for creating that. It's nice to see it realized in Chicago.
Great, thank you. I appreciate the plug.
Yeah, by the way, that's $20.
Dinner.
Yeah,
So
there you go.
let's talk a little bit about software. People tend to think that PLM is an old concept. How do we convey the value of greater visibility within the manufacturing process?
I'll let the PLM guys answer that.
All right. Well, I'll start, and then Jeff can finish it. So PLM, boy, that's a term. That's one of those product lifecycle management. What does it mean? To us, it means the entire product lifecycle. It's everything from starting with requirements, needs of customers, through your systems design, the concept design. When we think of this from a manufacturing perspective, we like to think of the concept to build. We want to create the design concept to build. We want to focus on being able to build that product, right? And often we engineers, we do the concept design and we wander off and we never even considered manufacturing. And then everybody talks about, well, the first 10 to 20% of the design drives 80% of the product cost. We haven't even talked to manufacturing and we've come up with our concept. So we really have focused on this concept to build, then design to build, plan to build, and then the build to deliver. The whole focus on this life cycle of manufacturing all the way through to product support. So the concept, I think, we've never really realized this complete thread from beginning to end. The technology and the capabilities of doing that are relatively recent. And I don't think PLM by any stretch of the imagination is old. I think it's frankly brand new. This ability to create these digital threads, to create this information from the concept all the way through field support.
Great.
When I look at it, just to add to that, David, this whole concept to mission. What is the mission that we're trying to accomplish in behalf of who's using this asset? And then being able to work upstream. So yes, you're going to figure out, how best to support that. And the industry solution experience was keep them flying, remembered. And then being able to, how are we going to manufacture it? And how do you do all the work from a design for manufacturability and all those type of activities, and then all the way up to the design and then the whole conceptual. So if you can imagine being able to create that virtual world, that digital twin right from the get-go, even though it may not be as mature during that conceptual development, but be able to begin that whole digital twin or 3D experience twin concept right from the get-go and take it all the way through its mission and be able to express that with the customer right there using all the different immersive and virtual and augmented technologies that are out there. And then once that is established and you can actually experience it in this very rich multi-physics environment, and then to be able to say, okay, now how are we going to build it and make sure that we can do that in the virtual world? How can we support it, make sure we can do that in the virtual world? And then how can we actually perform that mission and demonstrate that in the virtual world? So we now have the technologies to bring that whole life cycle all the way up front and to be able to express it in this very rich, immersive environment.
If I may, Greg, just add
Yes.
here, I think we need to remember that PLM is part of the picture. Every company has another system, and that's called ERP. Now, the ERP drives the accounting, the money, the customer orders, sometimes the production schedule. The ERP has no knowledge, per se, of the product design. It has a picture, a JPEG, but the product design is in the PLM, in the engineering tools. The problem there is that the engineering tools, they lack the schedule, they lack the knowledge of the customer, they don't have the deadline, it's not in there for production. So we have two big systems that are often, or too often, operated by different teams in different countries, different buildings, and they're not connected very well. And when you take it to the production floor, that's where the problem starts. It becomes a very rigid production floor, which is unable to adapt quickly to what's going on. Production order comes from the ERP, somebody takes it, runs to the PLM. I need to make this winglet today. Okay, PLM, tell me how to make it. What are the materials, what are the steps, what's the bill of process and bill of material? But then something happens. Material is missing or machine breaks down. And then what? So this is where the IoT can help. The IoT, the sensors, give us a lot of information of what really happened. And if you take that and compare it to the plan coming from the ERP and PLM, now we can start being a lot more dynamic and reactive or proactive on the production floor. So in that sense, and the PLM, the giants are bringing more and more of these capabilities, but we need to remember there's another force driving the production schedule, and that's the outside world, the customer, and that's typically driven via the ERP.
Great. So a couple of questions on supply chain. How do you see the digital thread or industrial Internet of Things extending into the supply chain, and how do small, medium-sized manufacturers utilize that technology?
I'll handle that.
Go
ahead.
No, I'll go. You go? No, you go.
Seniority first.
Oh, all right. I thought you were going to say good looks first.
No, that's him. So.
All right, so supply chain. Well, good Lord, guys, we buy, as a 70, 80% of what we're building, we buy. So you cannot ignore the supply chain. It's absolutely essential. So the technologies that we're working on and that worked on and developed in that space really are about being able to extend that digital twin and that digital thread down through that supply chain. Whether it's even their plant simulations or their product simulations, whether it's performance simulations, being able to integrate those from a systems perspective. Manufacturing is no different than a product, right? It's really a system of systems. I've got to integrate all of those suppliers into this. So that technology is foundational to a PLM. You've got to be able to do that with suppliers. It's absolutely critical. And it's not just handing off engineering information to them and expecting a part to show up on the front door. You need to understand their processes. What are their yields? What are their outcomes, right? There's nothing. I did the T6 trainer, and I once had a boss. He's CEO of the company, and we were struggling getting parts, and he asked me if it was an important part we were missing. And I had to think for a moment, because I was thinking, well, no, we've designed a bunch of unimportant parts on the airplane, and the one that we're missing is one of the unimportant parts. The point is, it doesn't matter. Every supplier, every item is absolutely critical, right? So integrating the supplier and bringing that information in and continuing the digital thread clear through the supply chain for whether it's requirements that are flowing down to them, the verification of those requirements, it's absolutely essential, and that's key to a PLM solution.
Well, it's something that we're already practicing with a number of our customers and partners such as GE and Airbus. And I'll explain. If we're talking about the digital thread, and if I'm the tier 2, for example, and I start from raw materials and I build a part. So if you recall, I have the entire family tree, the entire digital thread traced all the way back to the raw material. And now I ship the part to the next station in line. So I'm giving them a physical product, the part, but I'm also giving them the digital twin and the entire thread of a web of threads behind it. So at that point, my shipping station is just one stop before his receiving station, and then he takes that part physically and also the digital twin and continues to build on it, whether it's additional value add processes or taking another part and marrying them into an assembly, and then up the tier 1 all the way to the OEM. So Here, the technology actually enables something very powerful, especially if we take it to a central data center or up to the common discussion about the cloud. Whether it's a private or internal cloud for data security, it's not a question of integration anymore. It's not like I need to integrate my digital twin into his system anymore. We're always touching and linking to the same piece of software data. And that's very powerful, especially in terms of, now we're blurring the lines between the supply chain and the manufacturing chain. The fact that we're moving parts between different buildings or states or countries or across the ocean is a non-issue at this point. And we're talking about one long and very powerful thread from the end part, and imagine an entire airplane broken down into all the parts and all the twins and all the threads, all the way back to that first bucket of resin or first pre-preg 4 months ago in a completely different country. So this is very powerful, and we're starting to practice that, moving one step down and then the next step down as we do it.
So here's moving back into the industry application part of this. Where are the major gaps that you see in industry standards to apply to digital thread and to the aerospace industry?
Well, there aren't any.
Okay.
Almost. I think the DDMI organization is working to facilitate that, but we're seeing a lot of movement, whether it's companies like Dassault and Siemens and companies like GE, or even the industrial automation companies like Bosch and others, and it's converging. It'll take time, but maybe it's not a problem. Maybe the conceptual issues are enough. Remember, it's data, it's bits and bytes, and I expect, this is common, that these standards will consolidate, and even if they consolidate into a number of them, I think the industry will have to simply deal with that.
Yeah, I kind of think of a fundamental challenge with standards is that the technology is moving so quickly that the standards tend to lag the capability of the technology. So if there's one thing we industry need to do, it's we've got to get on our standards, ISO boards, the organizations that do this, and really drive them to be much more agile and quick. It's just the standards lag so much that meeting the standard never meets the customer's needs for exchanging the information. The technology has moved on and the standard is lagging. So we really do need to push and accelerate the ability to update standards. And everybody who's ever been involved in one of those knows that it's quite a political process to do that, but it's essential we industry step up and really drive that.
Yeah, one of the activities that we're doing when you think about airplanes, for example, every airplane has to be certified, whether it's with the FAA or EASA or someone. So the idea is that if we can create standards of processes, of methods, of tools, of rules, and so on, and be able to create these systems of work that leverage, the digital twin and leverage the sensing world that we're creating, and then be able to convey that to an organization like the FAA and have them come to a point where it's like, okay, yeah, I understand what you're trying to do from a processes and methods and rules, and then being able to certify those methods and rules that then can be applied to that airplane that will help the customer himself as they go through that whole certification process. So if we can shrink the gap, so to speak, from the concept through the actual flying of that particular aircraft, and be able to follow those rules and regulations and so on, and have them built into the system of work, then I think that's going to shrink the gap and take those life cycles that are 5 years, for example, from a certification standpoint, and shrink it to something significantly less.
Yeah, so what Jeff's really talking about are, a SAE standard. There's a ARP 4754, a standard for the way you certify an aircraft. So implementing that process, we've done that kind of a thing where we have a standard process that actually implements 4754 kind of to lead a customer through how would you do this. It's an approved methodology by EASA and FAA. I think those kinds of standards are that Jeff's pointing out, are essential to helping us speed. I think a lot of people, when we think of standards in this, have a lot to do with the supply chain and our customers, and that's really got to do with data exchange. And I would tell you that in general, that area, the standards lag our industry need for for being able to exchange information. It's just very difficult. Yeah, you meet the standard, but then everybody wants to exchange additive manufacturing information. Well, the standard doesn't do that, right? You know, composites still. There's some of the standards lag the needs in composites. So, so it's a real challenge, and it's something we as industry we've got to push on in order to be, I think, you know, as successful as we can be.
Okay. So, 2 questions on factories that I'm going to put together for you so that you can. So it's a really complicated question to answer. Fundamentally,
I thought we had a rule you couldn't do that.
I'm a professor. I can.
Yeah, I should have known. Should have known, Greg.
Fundamentally, what do you see as the next major leap in Industry 4.0, and will factories ever run themselves?
Okay, so I'm the old guy. No, they won't run themselves. Not in anybody's lifetime that's in this room, or probably even my grandkids' lifetime. There's something to be said for the gray matter that's between the ears, and there's no substitution for that. I think you're going to see a lot more adaptive and smart manufacturing. By that I mean, you know, if you look at it, we today, when we build aircraft, we build airplanes just like we did, you know, pretty much, well, I came from Raytheon Aircraft, Beech Aircraft. You know, Walter Beech would have recognized the way we still assemble airplanes today. He'd have been marveled by some of the equipment, you know, some of the robotics and et cetera. But in general, he'd have said, well, you really haven't done anything different than what we did in the 1940s. I think you're going to start seeing less fixed equipment, more adaptive manufacturing, flexible manufacturing, less equipment just building one kind of an assembly or a part. And I think you'll see an awful lot of that. But I think the real next generation in this is honestly, it's this, the Industry 4.0 principles of integration. Integration, 3 principles, and they all involve integration. It's going to be this data. How do I tie all of this information together, and how can I make smarter decisions such that my factory is optimized, my product is optimized? You know, those are, I think, the big next steps. Connecting engineering and manufacturing and being able to really do that seamlessly.
Yeah, I mean, one of the things that we're trying to do at our One Innovation Campus in Wichita is to be able to create this, what I call the sensing, scalable, flexible factory of the future, and being able to leverage robotics, cobotics in this very rich environment. So leveraging the immersive technologies of creating that system of work end to end, and then being able to take that virtual creation, that digital twin or a 3D experience twin, and bring it and manifest it into the physical world of this scalable, flexible factory of the future, leveraging Industry 4.0 principles and so on. And our goal, I mean, I'll just state it, our goal is to take a typical 3 to 5 year life cycle and be able to demonstrate how we could do that in 90 days, from concept to first flight in 90 days. So you're going to have to think differently. The system of work has to be different than the way it is today. These regulations, you got to figure out how to incorporate them and model them. So the reason why we built it is to create a new mindset of being able to think differently and what this future factory and what the future system of work from concept to first flight will look like. So it's an exciting challenge, and who knows if it'll, like you say, you know, we'll probably be dead. But I personally think that there's enough energy and there's enough capabilities that are out there that we have the opportunity to really make great strides in developing this type of capability going forward.
Well, I think, you know, we look at it in terms of optimization or pushing the envelope. You know, we deal with AI now in our company for many years, and, you know, it's like a big evil thing, but it's really not. It's all relative, and it's incremental. And if we have just automated a process, it's about taking it to the next level. The first speaker, Andreas Wollner, spoke about moving from 10 units a day to 100 or to 1,000. Well, that's great. So it's about pushing the envelope. If we are able to introduce this technology to help us make things better, faster, with higher quality, it probably means we can do more of it. And that's what this industry is experiencing. It is experiencing growth and a lot of challenges. So again, our mantra is the man-machine partnership, and the machine taking care of a lot of the mundane stuff, a lot of the routine, a lot of the noise, and escalating for decision and action, and that's where the person can always be ahead of it. And that's where we see it, that's our vision. 100 years from now, who knows, but who cares? The industry is very competitive, and you need to be one step ahead of your competition. And what is that optimal mix for your business model, for your demand, between the software, the machine, and the staff and management on the production floor?
So it seems y'all have captured some interest in here, because I've got a couple of questions now they want to get into specifics. So can you cite an example where you've assisted with the digital thread initiative using your technology, and what were the drivers that propelled that initiative? And follow that up with, what services do your companies provide to connect data, software, consulting, whatever, that you're using to help drive those initiatives?
Okay. Well,
You
sure.
go ahead.
When we talk about our solutions, we're always talking about tracking production and like I said, helping them make better decisions. So GE, as one of our customers, is using our solution, to better manage, track, and optimize the usage of composite materials. In that case, we're using RFID technology, not our own, it's commonly available, to track their materials and kits, and now soon tools on their production floor. Where are they? What's their situation? And so forth. When we track uncured material, obviously there's the question of shelf life, and perhaps that's the easiest example to give. If it's in the freezer, the shelf life clock stops. If it's out of the freezer, it ticks. And we're able to monitor the location and monitor the shelf life. Doing that automatically replaces the previous paperwork they had. And we see a lot of paperwork and Excel and whiteboards and paper tickets and a whole bunch of other stuff for doing that. But now we have a complete grasp, digital, accurate, and real time, of the exact shelf life of hundreds and thousands of materials and kits in production. And now we can take it up to the next level and raise an alert. And I can tell a supervisor, hey, Mr. Supervisor, hey, Mrs. Supervisor, you have a problem. Material number 1, 2, 3 in location A or B is about to expire in 15 hours. That's great. That's a lot better than they had before. And now they need to fix the problem. The better thing to do is, instead of telling them they have a problem, is helping them resolve it. So instead of, hey, supervisor, this material is about to expire, hey, supervisor, this material is about to expire, take it to machine number 4 on production line 7, use it for that job, remember the input from the ERP, and then you're able to resolve it, being proactive before it's done. So in this story here, and I think it's rather intuitive, we've replaced a paper-driven system, very manual intensive, very error-prone, with software. And again, it's perhaps relatively simple to explain, but there's a lot behind it. Again, that aversion of the complexity. What's all that algorithm behind it, calculating shelf life and expectation? That's not your problem, that's our problem. We see the reduction in waste, the reduction of cost of poor quality. They're not making parts anymore that they will scrap. We catch that ahead of time. And actually there's a pull from the production floor staff because they love it. They don't have to deal with the paperwork anymore, and it's all done for them. And now they're able to make more parts or do a better job with it.
Great. Others?
So I think the question kind of was the what drives these initiatives, and given a specific example. So any initiative ought to be driven by the business need, right? I mean, this is all about business. It's about being more competitive, winning more business, and then performing on that business. So key to that is the ability to execute, programs on cost and schedule, meeting all those technical requirements. The initiative that I can think of that we've done is we create a set of industry, similar to what Jeff was talking about, industry catalysts, specific operations. So this ARP 4754, we have a catalyst that a customer can install that will implement that process. In part of that, we do the whole verification of the requirements. So starting with requirements, whether they're FAA or EASA, tracing those to a method, whether it's going to be by analysis or by a test, and then completely tracing that through all the test articles and et cetera. What drove the company that we did this activity for, honestly, was their inability to certify products on cost and schedule. And they fundamentally were looking for a different way to go do business in order to be more competitive, save themselves an awful lot of money in certifying, and that was the business imperative. I think the most successful initiatives, when people think of any of these, they have a business imperative. If it doesn't have a business imperative, generally they struggle and kind of lose direction, maybe even come up with more point solutions than coming up with this entire digital thread kind of a solution.
I'm going to put a plug in for my colleague that's going to be speaking on Thursday. So on Thursday, come to Enrico. He's going to be talking about the future factory, and he's going to be giving some specific examples, okay, what we're doing with various customers. I'll summarize, at a minimum, the experiences that we've had is for every dollar that you invest in using these technologies and capabilities, at a minimum, you're going to get a $7 return. Okay, so, and I think it's greater, that at a minimum, I think for every dollar, a $7 return. So,
Great. So moving into a little bit different area, what are the implications of the digital thread for government defense acquisition, compliance, and reporting?
Geez, Greg, you should answer that one.
I'm just moderating. I asked.
No, come on now.
go ahead.
You're not going to touch that?
No, I'm not touching it.
You worked in the...
Certain things I'm not supposed to talk about yet.
Still classified?
So say it again.
So what are the implications of the digital thread for government and defense acquisition, compliance, and reporting?
So it's essential, right? I mean, but I think the real question here, honestly, is take a look at how we're going to sustain a product in the field from a government perspective, and how does the digital thread, go from the OEM down to the to the support, right? I believe that's essential, right? It's our products in A&D are unique in that their lifespans are huge. I mean, the B-52 will be, 90 when it comes out of service. Mm-hmm. The challenge in this is how do I know 20, 30, 40 years later why something was designed what it was, the way it was, why was it built that way, why was it expected? And that's all important if I'm going to be able to do service life extensions, I'm going to be able to understand how to service and support the product. So I think the digital thread probably has greater overall system cost reduction opportunities just based on being able to bring that down through the government to the support.
We talked about before, how would you write requirements for something that has to have a 50-year life in the field?
Yep.
So I think the world is going to the point where, because of these technologies, that I can create during that proposal phase, that I can create that very rich virtual system and demonstrate in the submittal of even the proposal how that system is going to be certified and satisfies all those regulatory requirements. So it's not about the paper, it's not about the digitization, but it's creating and providing, even upfront, that very rich multi-physics control sensing system that you can demonstrate to the government that it satisfies those certification requirements based on that specific baseline. I think we're going there. It's going to get better and better, because of the technologies that we have today. So it's very exciting to be able to see that mature and come to pass.
Great. So it looks like we're down to the end of our panel. I want to say I appreciate the input from you guys, and I thought it was a great session, and thank you for your time and willing to share. Thank you.
Thank you.